In this new unit, we'll be talking about transients. So far, we've assumed a couple of things about circuits that aren't necessarily true all the time. We've been dealing so far with something called steady state. Steady state means things don't change. This is fine when you're dealing with purely resistive circuits, or if you're dealing with capacitors and inductors without having to consider the fact that there is actual resistances in the circuit. And that's because in those types of circuits, things change instantaneously. On the other hand, when we have transients, what we mean is small events where things are changing. Typically, this will lead to steady state. So, for example, if I were to turn on my light switch, there's actually quite a bit of complex electricity going on in the first few milliseconds that eventually energizes my light bulb and fills my room with light. In this unit, we're interested in looking at what happens in those first few little whiles before everything settles down. Those things are called transients. Today, we're going to look at something called an RC circuit: resistor, capacitor. We know that capacitors can store energy, and therefore the capacitor might charge or discharge. And it's doing that through a resistor. Today in particular, we'll be looking at RC circuits that are discharging. The reason being that the math is a little bit simpler, but the concepts are all the same. So, what circuit is it that we're looking at? Here's a capacitor, there's a switch, and a resistor. Typically, the switch closes, and usually that's at time t equals 0, although it doesn't have to be. And finally, we assume that initially our capacitor is charged to some voltage. So, what does this look like? We assume that the initial voltage Vc at 0 is some voltage V0. And now our question is, what is Vc as a function of time? Now luckily, we still have all of the tools that we know from the previous units. However, we're going to need to solve a differential equation. Let's take a look. The first thing I'm going to do is redraw the circuit with the switch closed. It's easier to do it that way, so we don't need to consider the fact that the switch might be open, might be closed. We're just making the decision that it's going to be closed and current's going to flow. Let's consider this node here, the top of the circuit. I'll have current, I, flowing from the capacitor into our node, and the same current out into the resistor. I can now use KCL. C dVc by dt plus Vc over R is 0. And the key here that we need to keep in mind at all times is that Vc is actually a function of time. But at the moment, this function is unknown. So, we have an equation that relates an unknown function and its derivatives. We have what is known then as a differential equation. Now, what's important to know about differential equations is that they're actually quite a large field of study. I'm going to leave a lot of it to math class. What we're going to do is make an assumption about what Vc of t must look like. If you don't like it, maybe the assumption is a little bit too complex, I'm going to have to ask that you take a look at a math textbook. I'm going to claim that Vc of t has the form k, some unknown constant, e to the s t. I'll give you a little bit of a hint as to why it might look like that. When we rearrange our equation, we end up with negative Rc dVc by dt is equal to Vc. The unknown function is equal to a constant times its own derivative. The exponential has that property. So, I do promise you this is the correct form. But if you'd like a little bit more information about exactly where it comes from, math class is where you need to go. So, we have these two unknown constants, k and s. We need to solve for them. Let's take a look at how we might be able to do that. Normally, there's a multiple step process. In this case, we're only going to be using 2 steps because we only have 2 constants. The first thing we'll do is we'll use our initial conditions. We know that Vc of 0 is that V0. The capacitor was initially charged. If that's true, then V0 is also k e to the s times 0. But e to the power of 0 is 1. So V0 is k. That's fairly handy. Now what about s? Our next step is to plug it in. So, remember, the form is Rc times s V0 e to the st equals V0 e to the st. If you don't believe me, plug this in for v of t to our original equation, take its derivative, and try to see what you end up with. We now need to algebraically solve for s. Well, luckily, this will go away. This can go away. So we're left with negative RCS equals to 1, or S is negative 1 over RC. Very commonly, what we'll find is that we allow the variable tau equals to RC, and this is called the time constant. Therefore, S is negative 1 over tau. And Vc as a function of t is V0 e to the negative t over tau. So, what does this look like? If we plot Vc against time, initially we start at V0, and then it exponentially decays. As t goes to infinity, Vc of t is going to be 0. And this is what we mean when we say transient. This part here is a transient decay. If we plot this now on a very, very long time scale, we might see it decaying and then essentially being 0 for the rest of time. This part here, where things aren't really changing much, is the steady state. In this case, our steady state is 0. In the next few videos, we'll be expanding this to charging RC circuits and then RL circuits.